Hello students, and a very warm welcome. Today, we're going to get into a very important topic for your board exams, the methods of preparation of carboxylic acids. So let's dive right in and make sure this is crystal clear for you.
But before we start, here's a small question for you. Have you ever wondered how a key ingredient for a common pain reliever like aspirin is actually made in a laboratory? Well, the answer to that question is hiding right inside today's topic. And by the end of this short session, you will know the exact chemistry behind it.
So why do we need to learn so many different methods? Think of a chemist like a builder. Before constructing any building, a builder needs a proper blueprint, right? For a chemist, understanding these preparation methods is exactly like having that blueprint. It helps them plan out how to create complex molecules for things like medicines, industries, and research.
Now, what is the core idea behind all these methods? At the simplest level, most ways of preparing a carboxylic acid are all about one thing: taking a carbon atom from a lower oxidation state and stepping it up to a higher one. It's basically a step-up process.
A really great way to visualize this is to imagine something called an oxidation ladder. You can think of this ladder as the main highway, the most common route that chemists take to prepare carboxylic acids. Let's see how it works.
So the ladder starts at the bottom rung with a primary alcohol. Now, with a little push from a strong oxidizing agent, that's just a chemical that helps remove electrons, it climbs one step up to become an aldehyde. But if the agent is strong enough, it doesn't stop there. It keeps climbing all the way to the top, reaching its final destination, the carboxylic acid.
And what's really happening at the molecular level as we climb this ladder? Well, it's a transformation. We are breaking the old carbon-hydrogen bonds in our starting molecule, and we are building new, stronger carbon-oxygen bonds until we get that final COOH group. Okay, now this is a very, very important point and a common place for confusion. What about secondary alcohols? Can they also climb this ladder all the way to the top? The answer is no. You see, a primary alcohol has two hydrogen atoms on its main carbon, which allows it to take two oxidation steps up. But a secondary alcohol, it only has one such hydrogen, so its journey stops after just one step at the ketone stage. It simply cannot form a carboxylic acid this way. This is a key difference and a favorite question in exams, so please make sure you understand it properly.
And here's a beautiful way to see this process happen right in the lab. Imagine you take ethanol, which is a primary alcohol, and you add potassium permanganate. You will see the bright purple color of the solution just disappear. And if you smell it, you'll first get a sharp smell of an aldehyde. But as the reaction continues, that smell changes to the sour, familiar smell of vinegar, which of course is acetic acid. It's a complete visual and sensory confirmation of our oxidation ladder.
But what if climbing the oxidation ladder is not the best option? Maybe your starting material isn't a primary alcohol. So what do? This is where a chemist gets creative. There are other clever routes, or you can call them detours, that we can take to reach our destination. And these aren't just backups. They are very powerful tools for specific jobs.
Let's talk about one such powerful method, which actually has a bit of history behind it. Back in 1912, a chemist named Victor Grignard won the Nobel Prize for discovering a special chemical tool, the Grignard reagent. And even today, more than 100 years later, this discovery gives us an amazing way to build carboxylic acids simply by adding carbon dioxide.
So how does it work? Well, the Grignard reagent is what we call a powerful nucleophile, which just means it's very good at finding and attacking atoms that have a positive charge. When you add it to dry ice, which is nothing but solid carbon dioxide, it attacks the carbon atom and forms a brand new carbon-carbon bond. Then, in a final step, you just add some acid and you get your carboxylic acid. And remember our aspirin question from the start? This method is a key way to prepare salicylic acid, which is the starting material for making aspirin.
Another very useful path starts with something called a nitrile. A nitrile has a very strong carbon-nitrogen triple bond. By simply heating it with water in the presence of an acid or a base, a process we call hydrolysis, we can break that strong triple bond and convert it directly into our target carboxylic acid. It's another excellent and reliable tool for our chemist's blueprint.
So the most crucial point to understand is that you now have a toolkit. Depending on what starting material you have and what final product you want to make, you can choose the most efficient path to get the carboxylic acid you need. Let's just quickly summarize these paths.
This table is a perfect revision map for you. It lays out all our main routes very clearly. So how do you choose which path? It's simple.
If you have a primary alcohol or an aldehyde, oxidation is your direct go-to method. But what if you need to make the carbon chain longer by exactly one carbon atom? That is the special power of the Grignard route. It adds a carbon. And if your synthesis starts with a nitrile, then simple hydrolysis is the most direct path. You see? 4 different starting points, all leading to the same valuable product.
So, to wrap up, what are the key things you should take away from this? Just remember the core idea of the oxidation ladder, that picture of climbing up from a primary alcohol to a carboxylic acid. And remember that you also have other powerful paths in your toolkit, like the Grignard route for adding a carbon, which is used to make ingredients for medicines like aspirin. If you can just hold on to these mental pictures, the ladder, and the map with different paths, this topic will feel much, much lighter in your exams. You now have the blueprint.